Alright, so we're here to talk about graphing exponential functions today. So we're going to start off by graphing a function f of x equals 2 to the power of x. And you'll notice my notation up here at the top says f of x equals b to the power of x, where b is any real number greater than 0 except 1. So we're talking about values of a base value that could be 2, it could be, a half, it could be 5/3, it can be any number that's greater than 0 and not equal to 1. So my first graph is for b greater than 1. So I chose the value of 2. And I'm simply going to make a t-table of values, and I'm going to plot these and see what happens. Alright? So I'm just going to choose -2, -1, 0, 1, and 2. And I'm going to plug these in. Now I'm going to start at the bottom of the t-table because I think this is easier for most people to see. So if I plug in 2, I get 2 to the second power, which is 4. If I plug in 1, I get 2 to the first power, which is 2. If I plug in 0, I get 2 to the 0 power. Okay, so think about that. 2 to the 0 power equals 1. If I plug in -1, I get 2 to the negative first power. And that's the same as flipping this guy over and saying that I have 1 over 2 to the first power. All a negative exponent does is tell me to flip my base value to the other side of the fraction bar. Okay, so that would be 1/2. 2 to the negative second power, again I would flip that over, that would be 1 over 2 to the positive second power, which is 4, and this would be 1/4. Alright, so let's plot those values and see what's going on here. So at -2 I'm at 1/4, at -1 I'm at 1/2, at 0 I'm at 1, at 1 I'm at 2, at 2 I'm at 4. Anybody want to guess where we're going to be at 3? Yeah, we're going to be at 8. Alright, so at 3 I'll be at 8, and so on and so forth. Now, what about -3? What if I went to 2 to the negative third power? Can you take a guess at what that would equal? This would be 1 over 2 to the third. Well, that's an 8. Okay, so now at -3 I'm at an 8. And if I did 2 to the negative fourth, that would be 1 over 2 to the positive fourth. That would be 1/16. And I could keep going and going and going, but I'm never going to reach 0 here. And the reason I'm never going to reach 0 is because there's no value that I can plug in for this exponent. No value of x will make 2 to the x equal to 0. It's impossible. Okay? You will never be able to find a number that will make 2 to the x equal to 0. So that means that as I go to the left, I'm just getting closer and closer and closer to the x-axis. And as I go to the right, I'm getting bigger and bigger and bigger. Not only is x getting bigger, but y is getting bigger. Okay? So we're going to talk about some notation that we've seen before. What happens to f of x as x approaches infinity, as x goes to infinity? Well, as x goes to the right, my y values are moving up. So y is going to infinity. Alright? What happens to f of x as x approaches negative infinity? As x goes to the left, my y values are getting closer and closer and closer and closer to 0. Okay? So they're going down, but they're never going to go below 0. So y is approaching 0. Okay? Now if I look at this graph, it says what are the domain and range? Well, the domain, again, I can continue to plug in positive values of x and negative values of x, so my domain is x in the set of reals. However, my range, because I'll never go below the x-axis, that means I'll never get to a y value of 0, but I'll hover over 0. So I could say I'm above 0, and then my graph goes up forever to infinity, so I could say 0 to infinity, or I could simply say y is greater than 0. Okay, so that would be two different ways to do that one. So that is what the parent function of y equals 2 to the power of x looks like. Okay, so now let's take a look when we have a fractional value for the base. Okay, so again, we're graphing f of x equals b to the x, and now our b value is a value between 0 and 1. Okay, So again, I'm going to start off with the same t-table as before. We'll do -2, -1, 0, 1, and 2. And I would encourage you to stop the video, plug these in, see if you can do them on your own. Again, I'm going to start at the bottom of the t-table. I'm going to do 1/3 raised to the second power, which is a third times a third, which is a ninth. So at 2, I'm at 1/9. 1/3 to the first power is just going to be a third. 1/3 to the 0 power. Think about that one if you didn't shut off the video earlier. 1/3 to the 0 power is 1. Okay? Anything to the 0 power is 1 except 0. 1/3 to the negative first power. Now we talked about the negative exponent in the last example. What does a negative exponent do? It flips my fraction over. So this becomes 3/1 raised to the positive first power. Well, that's 3. And then I do the same thing with -2. I do 1/3 to the negative second power. The negative exponent says flip over the number that it's attached to. I'll flip over 3/1. I'll raise it to the positive second power, and that equals 9. All right, so here we go. At 2, well, going from the negative side. So -2, I'm at 9. At -1, I'm at 3. So I dropped rather quickly. At 0, I'm at 1. At 1, I'm at a third. And at 2, I'm at a ninth. Now again, think about your base value. Your base value is a third. I cannot raise 1/3 to any power of x and ever make it equal to 0. So as this graph drops this time, it's going to get, again, closer and closer to the x-axis, but it's never going to touch the x-axis. So as x approaches infinity, so as x goes to the right, my graph gets closer and closer and closer and closer to the y-axis, which is y approaches 0. Okay, but it never touches it. What happens to f of x as x approaches negative infinity? So as x goes to the left, my y values go up, and so we would say that y approaches positive infinity. What are the domain and range? Well, it's the same thing as last time. The x's go on both sides, left and right, so we would say x is in the set of reals. The range is, again, you could say it as 0, infinity, but we're not touching 0, so we're going to use a parenthesis. Or again, we could say that y is greater than 0. All right? So these two graphs look the same, but they just kind of look like they're flipped over versions of each other. Okay? So this graph down below here, this is what we call exponential decay. Exponential decay. It's called decay because as x grows, y gets smaller. Okay? Think of it as, an element. If you've been in science class and you've talked about decay, the half-life of something. That's an example of exponential decay. And so anytime something is going down in value, it's decaying. And that's exactly what's happening here. As x gets bigger, the y values are getting smaller. The graph up above is an example of exponential growth. Exponential growth. Now, this is the kind of growth we want to see if we put our money in the bank. It's unrealistic, but that's what we'd love to see if we stuck our money in the bank, is exponential growth like this, because everybody would be a millionaire at that point. But unfortunately, that doesn't happen. So as x gets bigger, y gets bigger, and you'll notice that as x gets bigger, my y values, for instance, if you were to look at the slope from 1 to 2, or from 1 to, let me try and say that again, from 0 to 1. If I was to look at the slope right here, my slope is 1/1. But then when I go from 1 to 2, my slope is 2/1. And then I go from 2 to 3, and all of a sudden my slope is 1, 2, 3, 4/1. So that's why it's called exponential growth, because the slope is growing at a much faster rate each time you plug in a different value or a bigger value of x. All right? All right, so let's keep going here. All right, so when we graph exponential functions, they work very much like other functions that you've seen. Parabolas, absolute value, things like that, where they shift left, right, and up, down, of course. So when we look at exponential growth or decay, okay, we want to look at it in terms of how did it shift. It's much easier to graph something if I know where it's shifted to. So when we look at a function, we're going to be looking at all of these functions, and I'm just going to put one up here at the top, y equals, and I'm just going to call it base value b to the power of x minus h plus k. Now hopefully the h and the k look familiar, because the h is the value that moves you left or right, okay? So h moves the graph left or right, just like it did when we were graphing parabolas earlier in the year. Absolute values earlier in the year. K moves the graph up or down, just like a parabola would move up or down. Okay? And in an exponential function, we call that shift the point where we shift. Like on a parabola, we call it the vertex. On an absolute value, we call it the vertex. Okay? We also did square root functions where it wasn't necessarily a vertex, but it, we called it a starting point. On an exponential function, we call this a critical value. So the critical value of an exponential function is the value of x that makes the exponent equal to 0, just like it would do when you shifted a parabola. So when I look at this first function here, I see the minus 1 up here. So right away I see a shift of right 1 and up 5. Now, here's the thing. If you go put a point right now at 1, 5, you're now incorrect. So you have to think about what's going to happen as I plug in some of these values. Now, this shift that I just talked about, absolutely. Does this graph move right 1 and up 5? It certainly does. But you have to understand where your initial critical point was on the graph of the other functions that we already did. So I'm going to scroll back for just a second and talk about that critical point. All right? So I'm just going to go up to this one here. On the graph of y equals 1/3 to the power of x, this value right here, okay, so if you look back at that definition on the other page, it said the critical value is the value of x that makes your exponent equal to 0. Well, there's where my exponent is equal to 0 right there. So my exponent is equal, you can kind of read that, exponent equals 0 right here at 0. Well, the y value was not 0. You can see that there was no plus or minus k to the outside here. The y value wasn't 0. The y value was 1. That's this point right here at 0, 1. So when we talk about a shift, we're talking about shifting that point right there, left or right, up and down. Okay? So just kind of watch as we go through here. All right? So my critical value, oops, too far. Let me see if I can get back to where I'm supposed to be here. There we go. So my critical value here, I want to look at what's going to make the exponent equal to 0. That's 1. Okay? Now, if I plug in 1, look at what happens. I get 3 to the 1 minus 1 plus 5. Well, 3 to the 1 minus 1, that's 3 to the 0. And 3 to the 0 is 1. And 1 plus 5 is equal to 6. So my critical value is 1, 6. And then my graph would be either going up or down from that point. Okay? So the next thing I want to do is I want to tell whether each represents growth or decay. All right? And so growth is when my base value, scroll over here, this first one represents growth, just like our first graph did, because growth happens when my base value is greater than 1. All right? So when b is greater than 1, I'm trying to figure out how to say this very quickly and shortly. When b is greater than 1, the graph is growth, and likewise when b And I'm going to write this, and hopefully you're going to understand. When b is less than 1, but remember the restriction on the other side was also greater than 0, so when b is between 0 and 1, so we're talking about a fraction, a half, a third, 4/7, things like that that are less than 1. When b is between 0 and 1, the graph is decay. All right, so I know that this first one is growth because the base value is bigger than 1. I know that my critical point would be 1,6. I go to the next one. I see a fractional value. This fractional value is between 0 and 1, so this would be decay. The value that makes my exponent equal to 0 is -2. If I plug -2 into the exponent, it's obviously going to go to 0. -2 plus 2 is 0. Well, what is 2/5 to the 0 power? It's 1. So 1 take away 4 is going to be -3. I go to the next one. This is exactly like our first graph. It's growth. Same base value. My critical value is going to be x equals 4. If I plug in 4, I get 4 minus 4, which is 0, and 2 to the 0 is 1. So now, if you compare this graph to the very first one of y equals 2 to the x, y equals 2 to the x had a starting point at 0, 1. Well, take a look at the shift on this graph. This graph is shifted to the right 4 units, still has a critical value at a y value of 1. Okay? Next one, I see a fraction, so I'm thinking decay. But then I look closer at the fraction, and that fraction is bigger than 1, so I know that this is growth. How do I make this exponent equal to 0? The only value that's going to make x equal to 0 is 0. So this graph has no left or right shift. I plug in 0 for the exponent, I get 3/2 to the 0 power, which is 1, and 1 take away 2 is -1. Next one, this is definitely decay. 1/9 is a very small number. So this is decay. My exponential value for the value of x is going to be -2. If I plug in -2, I get 1/9 to the 0 power, which is 1, and 1 take away 7 is -6. All right? Okay. So, I guess I already listed the critical points up here. Horizontal asymptotes. All right. So let's talk about horizontal asymptotes for these functions here. Excuse me. Now, when we talked about this function shifting to the left and the right, you will notice that my first point was not 1,5, it was 1,6. That's because every time I graph one of these exponential growth or decay graphs, I get a horizontal asymptote. That's what the k value tells me. So this k value is also the value of the horizontal asymptote. At y equals k. So if k is positive, we have a horizontal asymptote at a positive value. If k is negative, we have a horizontal asymptote at a negative value. So my horizontal asymptote here is going to be y equals 5. My horizontal asymptote here is going to be y equals 4. Excuse me, -4. The next one, there's no plus or minus on the end here. There's no k value out there, so it's going to be 0. The next one's y equals -2. And the last one's y equals -7. Okay? All right. So, it says graph the function f of x equals 3 to the power of x minus 1 plus 5 by finding the critical value of x. Then set up a t-table around the critical value and find other points. Graph the horizontal asymptote. All right? So the first thing I see is I see a critical value of x equals 1. Because again, I'm looking at what makes this guy equal to 0. Okay? So x equals 1 would make that exponent now equal to 0. My critical point then comes from when I plug in 1 to the function. So if I do f of 1, I'm going to get 3 to the 1 minus 1 power, which is 0, plus 5. Well, again, 3 to the 0 is 1, and 1 plus 5 is going to give me 6. So there's my critical point. I'm going to take that point and I'm going to put it in the middle of my t-table. Kind of like if we were graphing a parabola, we would put the point in the middle of the t-table as well. Then we're going to set up a t-table around that critical point in order to graph this. So we're going to go to the left of -1, so we're going to go to 0 and -1, and then we're going to go to the right of 1 and graph 2 and 3. Alright, so we're going to plug each one of these in. Here we go. Alright, so I'm going to start at, we might as well start at the bottom of the t-table. It's usually a little bit easier. F of 3. Alright, so here we go. We're going to do 3 to the power of 3 minus 1, which is going to be 2, plus 5. That's 9 plus 5, which equals 14. Not even sure that's going to fit on my graph. Plug in 2. F of 2 equals, plugging in 2 for x, 2 minus 1 would be 1, so that's 3 to the first, plus 5. So that's 3 plus 5, which is equal to 8. Definitely graph that one. Next one, we're going to plug in 0, so I get f of 0. Now this time I got to be careful, because when I do 0 take away 1, I get 3 to the negative first power plus 5. And so 3 to the negative first power is 1 over 3 to the first power plus 5, which equals 5 1/3. And then finally -1, f of -1 is equal to, so this time we're plugging in -1 for x, so -1 minus 1 is going to be 3 to the negative second power plus 5. Again, I'm going to flip this over. I'm going to call this 1 over 3 to the second power plus 5. And that's 1/9 plus 5, which equals 5 1/9. Alright, so there we got it. Let's graph those. Alright, oh, let's look at horizontal asymptote here too. Horizontal asymptote. I'm going to go back to my function. This plus 5 out here, so it tells me that I have a horizontal asymptote at y equals positive 5. Alright, let's go ahead and graph that. Here we go. Positive 5 for the horizontal asymptote. Graphing the points in the chart, we can't fit 314. We can definitely fit 2, 8. We can fit 1, 6. And 0, 5 1/3. Graph's a little small, -1, 5 1/9. Now, if I look at those points, as x increases, y increases, this is exponential growth. I should have known that already, because the base value from my function was positive 3, and so therefore I know that this graph is going to grow. Okay, that's it for today.